Hello everyone. In this lecture, I will make a brief introduction to LiDAR technology. LiDAR stands for light detection and ranging. This active remote sensing system uses lasers. A laser is a device that generates a stream of high-energy particles, termed photons, in a narrow wavelength band, light amplification by stimulated emission of radiation. Low-power lasers are used in a variety of consumer products such as CD players. High-power lasers are used in precise industrial cutting tools and weaponry. LiDAR systems use medium-power lasers. First optical laser developed in 1960. First airborne laser ranging tried out in 1960. First in late 1980s, the use of GPS made accurate range measurements from airborne laser profilers possible. Beginning of 90s, profilers replaced by scanners, and GPS combined with INS. Since 2000, ALS increasingly used in practice and in various applications, increasing scientific investigations and tests and better methods, continuously improving ALS systems, full waveform and simultaneous double ALS, more service providers and users. Since 2014, UAV LiDAR is more and more popular, more and better software. LiDAR systems use three technologies: laser ranging for accurate distance measurement, satellite positioning using GPS, inertial measurement unit to record orientation. Laser ranging device are used to record distance to target. GPS, differentially corrected, provide cm accuracy of aircraft. The IMU record roll, pitch, yaw of aircraft. LiDAR systems used for topographic mapping use eye-safe near-infrared laser light, mostly at 1060 for nanometer. Blue-green lasers centered at approximately 530 to nanometers are used for bathymetric mapping due to their water penetration capability. What LiDAR is? LiDAR is active sensing system. It uses its own energy source, not reflected natural or naturally emitted radiation. LiDAR is ranging of the reflecting object, based on time difference between emission and reflection. LiDAR is generating point clouds with X, Y, Z position. LiDAR is day or night operation except when coupled with digital camera. LiDAR is direct acquisition of terrain information, whereas optical photogrammetry is inferential. LiDAR is able to partially penetrate trees. LiDAR can penetrate openings in the vegetation cover but cannot see through closed canopy. LiDAR is not all-weather. The target must be visible within the selected EM spectrum. No rain or fog. Must be below clouds. LiDAR is not able to penetrate closed tree canopy. LiDAR can penetrate openings in the vegetation cover, but cannot see through closed canopy. The LiDAR instrument consists of a system controller and a transmitter and receiver. As the aircraft moves forward along the line of flight, a scanning mirror directs pulses of laser light across track perpendicular to the line of flight. The point spacing, pulse repetition frequency, flying HT and speed, scan angle, laser footprint. Demand is also influenced by many factors, such as flying HT, beam divergence, in ideal case a circle, in reality an ellipse or even more regular pattern. LiDAR systems can emit pulses at rates larger than 100,000 pulses per second, referred to as pulse repetition frequency. A pulse of laser light travels at the speed of light. LiDAR technology is based on the accurate measurement of the laser pulse travel time from the transmitter to the target and back to the receiver. Where R is the range between the LiDAR sensor and the object. The range R can be determined by rearranging the equation. LiDAR remote sensing avoids the problems of aerial triangulation and orthorectification because each LiDAR posting is individually georeferenced. However, it takes substantial processing to turn the laser range information into georeferenced MUS points, Some of the most important variables used in the processing include X, Y, Z location of laser in n-dimensional space at the time of the laser pulse, attitude of the laser at the time of the laser pulse, scan angle of the LiDAR at the time of the laser pulse travel time from the LiDAR instrument to the target and back. If we knew position X, Y, Z of the aircraft, we also know the pitch, roll and yaw. Range is measured. Angle is measured. Then we can derive the position X, Y, and Z. Thus far we have collected GPS data, IMU data, and sent and received laser pulses. How are these data turned into digital elevation values at specific X, Y, and Z locations on the surface of the Earth? This is accomplished through LiDAR post-processing, which takes place after the aircraft has landed. Post-processing software is used to associate LiDAR antenna X, Y, Z position, antenna roll, pitch, and yaw orientation. LiDAR range information into a set of latitude, longitude, and altitude coordinates for each LiDAR return. The output is typically in a compact binary format of WGS80 for coordinates, with options for converting the output to ASCII formats and/or UTM coordinates. Through the processing we can produce point cloud. The range measurement process results in the collection of elevation data points, arranged systematically in time across the flight line. The example displays MUS points associated with the ground, several power lines, a pole, and tree canopy. A laser pulse can have many returns. The first return, some intermediate returns, and the last return. The first returns, the second returns, the third returns, the fourth returns. LiDAR intensity is geo-referenced. Backscattered intensity of reflection for each laser pulse. Loss is standard LiDAR point data format. For each point in the loss file, it has many attributes, such as X, Y, Z, intensity, return number, number of returns, scan direction flag, edge of flight line, classification, scan angle rank, user data, point source ID, GPS time, RGB and alpha. As per standard LiDAR point classes: 0, never classified; 1, unclassified; 2, grounded; 3, low vegetation; 4, medium vegetation; 5, high vegetation; 6, building; 7, low point; 8, high point or key point; 9, water. This is a point cloud is covered by the image. Point cloud can produce many products, such as DSM, DEM, true orthophoto, contours. Point cloud filtering is a key step in point cloud processing. Filtering is named as classification of points into ground and non-ground. LiDAR has many applications. For example, mapping of corridors, mapping of electrical transmission lines and towers including tree clearance, DSM and DTM generation, measurement of coastal areas, high accuracy and very dense measurement applications, for example, flood mapping, DTM generation and volume calculation in open pit mines, waste deposits, 3D mapping of important infrastructures, DTM and DSM generation in urban areas, automated building extraction, generation of 3D city models, rapid mapping and damage assessment after natural disasters, for example, after hurricanes, earthquakes, landslides, measurement of snow and ice-covered areas, including glacier monitoring. Measurement of wetlands. Derivation of vegetation parameters. For example, tree height, crown diameter, tree density, biomass estimation, determination of forest borders. Ossoimage and true ossoimage generation. Hydrographic surveys in depths up to 50 to 70 meter. That's all. Thanks for your attention.